In this tutorial we're going to look at percentage yield. The first aim is describe how to calculate the formula mass, MR, for a molecule, then explain how to calculate theoretical yield and percentage yield, and finally explain how to calculate empirical formula. Have you ever considered what a bonkers idea farming is? It's hard to believe that at some point some humans decided to switch from just hunting and gathering food which was local to them to setting up a permanent farming site. What this meant was having a kind of vision that you'd plant something today and months down the line or weeks down the line you would have food. Now, bearing in mind that humans didn't survive very long in the wild back then, that's quite an amazing and bold venture. So a farmer would sow their seeds, and let's assume for a second that every single one of those seeds germinated and became a healthy, successful crop. A chemist would refer to that as theoretical yield, the maximum expected amount of product you hope to get. But the reality is many of those seeds won't survive, some will get eaten by birds and so on, and so the actual yield, how much you actually get, will be much lower. So a farmer will only get a percentage of the crops in relation to how much they expected to get. This illustrates the idea of theoretical yield and percentage yield quite well. But the bigger picture here is obviously the farmer can get money from this process, and chemists can get money from chemical reactions. So let's say you have this chemical reaction where you're reacting molecules A and B to get the products C and D. Is it worth doing this chemical reaction? A chemist would ask themselves. Here's the factors they would consider before they decide. Yes, it's worth it if I get a high percentage yield. In other words, a lot of what I put in turns into profitable, useful product, a bit like as many of those seeds germinating as possible. All the products are commercially useful, so there's no waste product. So let's say C and D both can be sold for money. And obviously, if the reaction's fast, then you can churn out a lot more product over time. All these things will bring a chemist profit and therefore are a good reason to carry out this reaction. However, perhaps some of these products are useless waste products and therefore they have no commercial value. Perhaps some are harmful waste products and therefore can damage the environment, and therefore disposing of these waste products can be expensive, and some may be unsafe and therefore dangerous. So these are reasons that would affect how much profit a chemist makes and therefore would turn them off doing this reaction. But one thing's for sure, there is a lot of money to be had in chemistry. So I'm going to first show you how to work out formula mass. That is the mass of the molecule. In this tutorial, I'm basically going to show you how to do something, then I want you to pause it and try it yourself. To help you with this activity, I've given you the relative atomic masses for the elements that come up in the question. Now, you will be able to find these in the periodic table in the front of your exam, but they usually also give them to you in the question that it applies to. So, we're looking at carbon dioxide first. Now, carbon dioxide has 1 carbon and 2 oxygens. Working out the mass of the molecule is really easy. All you do is add up the masses of each atom that make up that compound. So in carbon dioxide, I have 1 carbon, which has a mass of 12, and I have 2 oxygens, which have a mass of 16. So the mass of carbon dioxide, in other words, the MR, the molecule mass or formula mass of carbon dioxide, is 12 plus 16 plus 16, which gives you 44. Formula mass is nothing more than simple addition, so most students find it quite easy. So why don't you pause now and have a go at working out the formula mass for these molecules? Okay, here's the answer. Water, very easy. We have 2 hydrogens which have a relative atomic mass of 1 each, so we do 1 plus 1, and 1 oxygen, which is 16. So the formula mass for water is 18. Next, we have magnesium hydroxide. Notice that we have brackets here and a 2 there. That means everything inside the brackets must be doubled, but not the magnesium, because that's not inside the brackets. So we have 24 for magnesium, then we have 16 plus 16 for the oxygen but doubled, so 2 oxygens, and 1 plus 1 for the hydrogen but doubled, and that gives you a formula mass of 58. And finally, we have 2 molecules of potassium sulfate. So what I recommend for this one is work out the mass of potassium sulfate, ignore the 2, and then whatever it is afterwards, just double it. If you had a 3 here, then you triple it. So you're just multiplying this by the number of molecules indicated by the large number at the start of the molecule. In other words, we have 2 potassium, so 39 plus 39, you can see that here. We have 1 sulfur, so that's 32, and we have 4 oxygen, so 16 plus 16 plus 16 plus 16. But then, after we've worked that out, we multiply the answer by 2 because of this 2 here, so we have 348. That's about as complex as it gets, these two, so if you handle that, you can handle anything in an exam. So that is how you describe how to calculate formula mass. So now we're going to look at percentage mass calculations. Now this is where chemistry starts to become useful and we can start thinking about the idea of profit. So I'm going to do one example, then I'm going to give you a question, you pause it and try it out before I give you the answer. So let's say the question is around this idea. A mine has extracted this quantity of iron oxide, so 8 tons of iron oxide, but they want to find out, theoretically speaking, how much iron will they obtain from 8 tons of iron oxide? Because obviously iron oxide is a compound containing iron and oxygen. So if we remove all the oxygen, how much iron are we left with? And then we can decide, is it worth doing this? Is it worth extracting the iron? So what you have to do is effectively calculate the percentage mass of an element in a compound. So here we have iron oxide, Fe2O3. What percentage of iron oxide is accounted for by iron? So what proportion does iron take up of iron oxide? So start off by writing the formula, Fe2O3. And again, the question is very likely to give you the relative atomic masses of the elements in the question, but if not, just look at your periodic table. So the first key step is calculating the MR, the molecule mass of iron oxide. So we have Fe2, 56 plus 56 as given here, and O3 plus 16 plus 16 plus 16 to give you 160. So this is the MR of Fe2O3 of iron oxide. Next, you calculate the total mass of iron in the compound. So remember it's Fe2 here, so you have to add 56 to 56. That tells you that if iron oxide is represented by 160 units of mass, 112 of those units will be accounted for by iron. So just 56 plus 56, Fe2. And finally, you calculate the percentage of iron in iron oxide. So you take iron, the amount of iron, 112, divided by the total mass of the molecule, so 160. So you're getting the proportion of iron oxide, which gives you 0.7. Then you multiply by 100, and that gives you 70%. Now just have a look. 112 of 160, that feels like about 70%, so that figure seems right. Always look at it and just get a sort of feel for whether it's right or not. So we know that 70% of this iron oxide will be accounted for by iron. So if we have 8 tons of iron oxide, how many tons of those 8 will be iron? Well, it's simple. We just need to find 70% of 8 tons. To find a percentage, simply decimalize the percentage, so 0.7 divided by 100, and then times it by the quantity, so 8 tons. So 70% of 8 tons can be written mathematically as 0.7 times 8, and that gives you 5.6 tons. Again, get a feel for it. So 70% of 8 tons, well, that does feel like it should be around 5.6 tons, so that makes sense. So now I want you to have a go. The setup is this. If you have 500 grams of sodium carbonate, what mass will be accounted for by sodium? Here's the formula for sodium carbonate, Na2CO3, and here are the relative atomic masses of the elements in this molecule, in this compound. I'll leave these here so you can stop and pause and see what I've done to help you work out these bits. So pause now. Okay, so the first bit is calculate the formula mass of sodium carbonate. So you just do 23 plus 23 for Na2, 1 carbon plus 12 plus 3 oxygen, 16, 16, 16, which gives you a formula mass, MR, of 106. Next, you calculate the total mass of sodium in a compound. So in this compound, we have 2 Na, so 23 plus 23 is 46. Then calculate the percentage of sodium in sodium carbonate. So you do 46 over the mass of the whole molecule, 106, which gives you 0.434. Then you multiply that answer by 100, and that'll give you 43.4%. So that tells us that 43.4%, basically below half, just below half of this 500 grams will be accounted for by sodium. So we're looking for an answer below 250 grams, because that would be 50%, and we're looking for 43.4%. So 43.4% of 500 grams will be 0.434 times 500, which gives you 217 grams. So now we're going to look at how we calculate theoretical yield. It's another process to work through, so I'll do the same. I'll give you one worked example, you pause and try one yourself, and then I'll reveal the answers. Theoretical yield, if you have to explain what it means in an exam, is defined as follows. The maximum expected amount of product you hope to get from a chemical reaction. So in other words, it's how much your formula predicts you will get. So the question you get might be something like this. How much sodium sulfate do you expect to get when reacting 80 grams of sodium in excess sulfuric acid? Basically, you can read this question by cutting out the noise and just looking at what's important. How much sodium sulfate will you get in a reaction if you use 80 grams of sodium? Everything else is just noise, you can ignore it. The first step is write down the balanced symbol equation for the reaction, but normally they give you this in the exam, so normally I wouldn't have to worry about this so much. And that's because this skill isn't assessing your ability to balance equations, but rather work through this process. However, if they wanted to be mean, I guess you would have to do this as well. So we have Na plus H2SO4, sodium plus sulfuric acid, produces sodium sulfate and hydrogen. Now I've only underlined these two because we can ignore this. We can ignore this one because it says excess sulfuric acid. That means we have so much of it, we don't have to consider it, don't have to think about it, it's not going to limit the reaction, we have plenty of it. And hydrogen just isn't the thing we're looking to get, it's the unwanted part of this chemical reaction. So we're only interested in sodium and how much sodium sulfate we get. So you work out the formula mass for the relevant reactant and product, ignore the others. So ignore this and ignore this. So it'll give you the relative atomic masses probably in the question, but if not, look at your periodic table and you'll see that the formula mass for this, well, it's easy, it's just one sodium atom, so it's 23, but this one is sodium plus 1 sulfur plus 4 oxygens, which will add up to 119. So what this tells you is that if you have 23 units, it could be anything, grams, tons, kilograms, if you have 23 units of sodium, you'll get 119 units of sodium sulfate. So if you double this figure, let's say you had 46 units, you'd expect double this amount for sodium sulfate. In other words, 238 units. If you half this figure, then you'd have to half this figure. This one is proportional to this figure, so however much you step this up by, you must step this one up by the same amount. However, this figure here, 80 grams of sodium, we don't know. It's not a nice easy number. We can't double this to make 80 and therefore double that. So what do we do when we have an awkward number like this to figure out? Well, you divide to get 1. In other words, I'm scaling this down to 1. So to turn 23 units into 1 unit, I divide by 23. So now I have 1 unit of sodium. And because this is an equation, I have to do the same to this side. So I must divide this by 23. So if I do 119 divided by 23, I get 5.17. In other words, if I have 1 unit of sodium now, I know I'll get 5.17 units of sodium sulfate. But what if I have 80? Well, now it's easy. Now that I've got 1, all I have to do is multiply by 80 on both sides to scale it up to 80 grams. So you multiply this figure by 80, so this is now 80, but you do the same to the other side. You scale it up to 80, and that gives you 414 grams. So 80 grams of sodium will give you 414 grams of sodium sulfate. So the key thing here is, remember, when you've got the masses of the different molecules, you divide by itself in terms of 1, and then you scale up by the figure in the question. So mine said 80 grams. Don't let the unit phase you. It could ask you for tons, in which case you just replace grams with tons. So like before now, I'm going to leave my worked example here for you to apply to this question. You can pause it and work it out yourself. The question is as follows. How much magnesium oxide is produced when you burn 60 grams of magnesium in air? Now remember, the only two things that are important here are the amount of magnesium and magnesium oxide. The oxygen in the air is irrelevant because there'll be an excess amount of it. I'll do what the exams do. I'll give you the balanced symbol equation. So now pause and work out the rest. Okay, so we've got 2 Mg plus O2 gives you 2 magnesium oxide molecules. So firstly, you have to work out the formula mass for magnesium and magnesium oxide. Now magnesium has a mass of 24, but 2 magnesiums would be 48. You must take that into account as well, and magnesium oxide will be 2 lots of MgO. So in other words, 24 plus 24 plus 16 plus 16, which will give you 80. So we know that 48 units of magnesium will give you 80 units of magnesium oxide, but how much will 60 units of magnesium give you? Well, you divide 48 by 48 to scale it down to 1, but you must do the same to the other side. So 80 divided by 48, and that will give you 1.67. So for every 1 unit of magnesium used, you'll get 1.67 units of magnesium oxide. Now you just have to scale up to get 60. So to scale this up to 60, you multiply by 60 and do the same to the other side because it's an equation. What you do to one side, you do to the other. So it'll tell you that if you use 60 grams of magnesium, you react 60 grams of magnesium in air, you'll get 100 grams of magnesium oxide. So these figures here represent our theoretical yield, how much our formula tells us we should expect to get, the maximum amount we expect to get. However, in reality, when we perform a chemical reaction, we always seem to get less than we expect. So the actual yield, what we actually get, is always less than the theoretical yield, how much we expect to get. There are three reasons for this that you need to know. Firstly, not all the reactants in the reacting chamber may actually react, so some of them may be left unreacted. So because of that, you won't get as much as you expect. So incomplete reactions is one reason. Now let's say you've finished your reaction in the reacting chamber and now you have to transfer it. When you transfer chemicals, the chances are some will still be stuck within the original reacting chamber. Just like if you're pouring juice from one glass to another, some of the liquid will still be stuck to the sides of the original glass. So there are losses when transferring chemicals. And finally, how do you know that the reactants you are using aren't mixed in with some impurities you don't want? And therefore, when you react it, some of those impurities react to make products you don't want. And that would take up some of the mass. So actually, not all of what you have there is the product you expected. So impurities in reactants cause unwanted reactions. So the proportion of what you get in relation to how much you expect to get is called your percentage yield, all right? And the higher the percentage yield of a reaction, the more profitable it will be for a chemist to carry out. That's why this is important. How you do this is very simple, and it often comes up in exams. So you do actual yield divided by theoretical yield. Where students get mixed up is which one you put on top. So I tell them to think of the A team, so A first, T second. So actual yield divided by theoretical yield times 100. And that will give you your percentage yield. So for the example I worked out, I do 400 grams, because let's say that's what I actually got, and it will tell you that value in the question. You won't have to work that one out. The exam question will say, let's say you only got 400 grams of the 414 you were expecting. What's the percentage yield? So you do 400 grams divided by the theoretical yield, 414 grams, and then you times that answer by 100 to get the percentage. So we have 96.7% as our percentage yield. So for the one you worked out, let's say that the actual yield was 80 grams and not 100 grams. What would the percentage yield be? So let's see if you got it right. You do the actual yield, 80 grams, divided by 100 grams, the theoretical yield, which gives you 0.8, times by 100, 80%. So calculating percentage yield is really easy. And that's how you explain how to calculate theoretical yield and percentage yield. Finally, let's look at the idea of calculating empirical formula. So empirical formula is basically how you find out the formula of a molecule experimentally. But that won't make much sense until you see the method. Another way of thinking about it is the most simplified version of a molecule's formula. So hydrogen peroxide is H2O2. So you can see the ratio of hydrogens to oxygen here are 2 to 2. This can obviously be simplified to HO, 1 to 1, because why not? The ratio is still the same, proportion still the same. So the empirical formula of hydrogen peroxide is HO. That's about as easy as it gets. Let's see the more complex version. Once again, I'm going to show you one worked example, then you pause and try one yourself. So the question is, find the empirical formula for magnesium oxide if 16 grams of magnesium oxide is produced when reacting 9.6 grams of magnesium with air. And it should give you the relative atomic masses, but if not, go to your periodic table. So the first step is listing the elements stated by the question. So we have magnesium and we have oxygen, MgO. Step 2 requires you to write the experimental masses. So we know that there's 9.6 grams of magnesium, but we need to find the mass of oxygen. Now we only know the mass of magnesium oxide, which is 16 grams, but if we remove 9.6 from 16 grams, we'll be left with just the mass of oxygen. So 16 take away 9.6 will give you the mass of oxygen, which is 6.4 grams. Sometimes you won't need to perform that step, but I just thought I'd give you the more complex version so you're prepared. Next, you divide each of these masses by the AR, the relative atomic mass for that element. So For magnesium, you divide by 24, which gives you 0.4, and for oxygen, you divide by 16, they're written here, to get 0.4 as well. Then you multiply by 10 to get nice whole numbers, integers over here, and then you scale down or up to obtain the simplest ratio. This one's nice and easy. They can both be scaled down by 4 to get 1 to 1. So the empirical formula for magnesium oxide, as determined experimentally, is MgO. 1 magnesium to 1 oxygen. Your question is as follows. Find the empirical formula for the hydrocarbon molecule formed with a mass of 3.2 grams when 2.4 grams of carbon reacts with hydrogen. So a hydrocarbon molecule is one which just has carbon and hydrogen atoms. You know that the molecule has a mass of 3.2 grams, but 2.4 grams of those 3.2 grams are carbon. So pause and try it out yourself. Here are the relative atomic masses. Okay, so firstly list the elements. So we have carbon and hydrogen. Then you need to write the experimental masses. So 2.4 grams for carbon and 0.8 grams for hydrogen, because I've subtracted 2.4 from the hydrocarbon molecule mass, which is 3.2. So if 2.4 was carbon and we subtract it from this total 3.2, we'll be left with hydrogen only. Next, divide by the AR, the relative atomic mass for each element. So carbon you divide by 12. Hydrogen you divide by 1, and that gives you 0.2 to 0.8. Then you multiply by 10, that gives you 2 to 8. So every 2 atoms of carbon will react with 8 atoms of hydrogen to make this hydrocarbon molecule. Can we simplify this? So you just need to halve it to simplify it. So 2 halved is 1, so you do the same to 8, halve it. So every 1 atom of carbon will react with 4 atoms of hydrogen. So the empirical formula for this hydrocarbon molecule is CH4, in other words, methane. The bit which will confuse students or they might forget is this part here. You must remember to divide the experimental mass, the mass in the question, by the relative atomic mass. If you get those the wrong way around, you'll get the wrong answer. So please remember experimental mass on top divided by the relative atomic mass. Finally, the hardest empirical question I've seen so far in exams is when you had to work out the empirical formula for an iron oxide molecule. Now, when you divided the experimental mass by the relative atomic mass for each element, these are the figures you came up with. Now, we can't divide or halve those to make them 1, so it's immediately a bit awkward. But you can always scale up. So 0.06 to 0.08 is the same as the ratio 6 to 8. The point is here, I haven't multiplied by 10, but I've had to multiply by 100 to get these whole figures. So be aware that sometimes multiplying by 10 isn't enough. You might have to go one step further, depending on how many decimal points you're given. So this can be simplified as follows. You just halve 6 to make 3 and halve 8 to make 4. This is the simplest ratio you can get. So this molecule of iron oxide has the empirical formula of Fe3O4, and that's as difficult as it gets. And that's how you explain how to calculate empirical formula.